Hello YouTube, in this video we're going to explore reflections of trigonometric functions, and specifically we're going to be looking at the graph of y equals sine of x in this video, but just know this applies to all trig functions. And so let's go ahead and review what we know about trig functions. We say at least one of this form. We say y equals, we say capital A sine of bx. Some things that we picked up along the way, at least of this basic function y equals sine of x, is that it has a period of 2 pi and an amplitude of 1. So we're going to go out one period length on the x-axis, cut that in half, and then cut those halves in half. And then we're also going to go one up and one below. Okay? And we can just find all these values by looking at the unit circle that has a radius of 1. Of course, this would tell us the sine and cosine and sine values, respectively, of any angle. And at least these four we should know pretty quickly off the top of our heads. So we say there those four are for at least 0, pi halves, pi, 3 pi halves, and 2 pi. That's the same as 0 anyways. So we say going around this, we notice that sine at 0 radians starts at a height of 0, and the output at sine at pi halves is 1. So it's up here at its maximum. And we say now at pi it's back down to 0. At 3 pi halves, or 270 degrees, we're down at negative 1, and then we're back to a height of 0 here. So here's our one cycle of the sine curve. The question in this video we're going to be looking at is what happens when we kind of mess around with this a value. So you can see what's coming up next. We're going to double the a value that we had before. This was just 1 prior to this. But we say, and we're also going to make it negative. So on this graph, just know that we're not going to affect the period of this graph because we're only changing the a value here. So we're going to go out 2 pi still, cut that in half, cut those halves in half. Except for this time, I'm going to go up 2 and down 2. So you can kind of see where I'm probably going with this already. But if we were to make a table of values here, we would have to, when we find an angle to plug in, we'd plug it in, we'd find the sine of that first, and then we'd have to double it. So for instance, the sine at 0 radians is still 0, but if I take that times 2, I still get 0. So it starts down here. When we say going up to pi halves, the sine value is 1, but 1 times 2 is 2. So you can see how it's still going to go through this, and we're going to get 0 here. I'm going to get negative 1 is my sine value here, so double that, I get negative 2. And basically, I get the same curve. So recall that the a value out in front, when we talk about a function of this form, at least for a sine curve, it has an amplitude, and we say the amplitude is equal to the absolute value of a. So we can see that this has an amplitude of 2. This wave over here, actually, I'm going to comment before we graph it, it has an absolute value, negative 2 value of 2. So it's going to have an amplitude of 2, but we're going to affect the way it looks. We're going to go out, one period length, 2 pi. Cut that in half, this is pi, cut those halves in half, and I'll still go up 2 and I'll still go down 2 because I know that it has an amplitude of 2 by definition. But the difference here would be that when I find the sine value at 0, we get 0, and 0 times negative 2 is still 0. When we find the sine value again at pi halves, up here on our unit circle we say is 1, when we double that but with a negative 2, what happens is we get an output of negative 2 instead of a positive 2, whereas prior to this we got a positive 2. So we're still going to hit a height of 0 at 180 degrees or pi radians right here. And we're going to double that with a negative 2. Still get 0, but this one's going to pop up here this time to positive 2, and this one's going to come back to 0. So we get this wave. And if we notice this here, it is the same exact wave as this one here, except for it's been what we call reflected. So this is a reflected trig function. And we're going to notice here that the reason why this happened is because we had a negative a value. So when I ask these questions, I say, well, what do all these graphs have in common? They had the same period. We didn't change that at all. So it went through one full cycle in a 2 pi input value length. We say, what are the differences between these graphs? Well, we said the amplitude changed from graph 1 to graph 2. So amplitude changes. Okay. You could comment that the second two both had an amplitude of 2, but you could also say this. We say the last graph was reflected. Reflected how? We say reflected across the x-axis. Okay? So that being said, we say what generalizations can we make about the value of a function that has a negative a value? And so what we can draw is this conclusion here, at least conjecture, and you can see that it's always true when you test it. But we say if a is less than 0, this is if it's negative. Okay? We're going to have a reflected graph. So it basically means you're going to draw the same graph you normally draw. It's just that your points are going to be flipped over the x-axis. And if a is positive, it is a normal orientation. Okay, it's set normally. Cool. All right. So those are the conclusions we want to draw in this video. Just really quickly before we sign out on this one, we say any function y equals a sine bx, or y equals a cosine bx, or y equals a tangent x is going to be reflected if our a value is negative. Okay, so that's the conclusion we can draw here. Thanks.